Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through graphing exponentials. So what is an exponential? It's a graph of the form y equals a to the x. We'll also look at y equals a to the negative x and y equals negative a to the x. What makes it an exponential? You can see that the x is now in the power. It's not like y equals x squared, where the power was 2, the power was a set number. Now the variable x is part of the power. So let's look at how we might graph something first up, like y equals 2 to the power of x, 2 to the power of minus x, and we'll also look at y equals minus 2 to the power of x, okay? So just to illustrate why the graphs look the way they do, I'll go through a table of values, but hopefully you'll see that there's a general shape to them and you'll be able to graph them a little quicker. So remember, when we're using a table of values, we choose the values of x. So I've chosen negative and positive values of x so we can see what is happening on both sides of the y-axis. So we just substitute them in. So let's say x is negative 4. So 2 to the power of x is 2 to the power of negative 4. Remember, when we did negative indices, that's just 1 over 2 to the power of 4, or 1 over 16. So it's a very, very small number. Okay, so hopefully you also remember, when you raise a positive number like 2 to any power, it never equals 0, it's never less than 0. So if you get a negative answer, you've done something wrong. So 2 to the power of negative 3 is the same 1 over 2 to the power of 3. It's 1 over 8. Same idea for negative 2. It will be 1 over 4. 2 to the power of minus 1 is half. You can use your calculators for this. So remember, anything to the power of 0 is not 0, it is 1. 2 to the power of 0 is 1. And then 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 16. Okay, so hopefully you can see very clearly that this shape will not be linear. It'll be a curve, because when x is going up by 1, y is not going up or down by the same amount. So here, y is going up only slightly from 1/16 to 1/8. Here it's going up quite a bit. It's gone up by 8 when x has gone up by 1. So because when x is going up by 1, y is not going up by the same amount each time, this function will be a curve. It will not be linear. So let's look at 2 to the power of minus x. So if we substitute in x is minus 4 into it, so we have 2 to the power of minus x, change x, we're going to write minus 4 instead. Notice you now have two minuses, and they make a plus. So when x is minus 4, 2 to the power of negative x is the same as 2 to the power of positive 4, which is 16. Similarly, when x is minus 3, 2 to the minus x is 2 to the power of positive 3, which is 8. Again, you can put these in your calculator. So at 0, 2 to the power of minus x still equals 1, because anything to the power of 0 is 1. You can see that this row that I'm doing right now, the second row, is the same as the first, except the order of the numbers is reversed, and there's no coincidence about that. So if I want to do minus 2 to the power of x, it's the same as the first row, except the numbers will be negative. Because remember, if you have something like, so I'm going to do the first one, if you have something like, let's say, minus 2 to the power of minus 4, you do this first by order of operations. So 2 to the minus 4, we figured out was 1 over 16. We figured that out in the first go. So minus 2 to the power of minus 4 is just minus 1 on 16. So it's the same with all of these. You just take the number in the first row and it's going to be negative. Minus 1 over 8, and then minus a quarter, minus a half. So anything to the power of 0 is 1. So minus 2 to the power of 0, this equals 1. So the whole thing is minus 1. And so on. Okay? So none of these are linear, because when x goes up by 1, y does different things. So we can now plot these points. So let's first plot the first one, y equals 2 to the power of x. So I'll do that in blue. So when x is minus 4, y is negative 1 over 16. So that's a very small number. So it'll be like down here. You don't have to be like really accurate. And then minus 3, 1 on 8 will be about here. So that's a tiny bit more, the y value. Minus 2 1/4 is a tiny bit more again. Minus 1 1/2 is a tiny bit more again. So then we've got the point 0, 1 that goes through there. And we've got 1, 2, 2, 4, 3, 8, and 4, 16. So you can see that this one gets big really quickly. So what's happening is as x is coming from the negative side, as x gets more and more negative, the function gets closer and closer to the x-axis. The y value gets closer and closer to 0, but doesn't actually hit 0. Okay, and this is what it looks like. That's the general curve. So y equals 2 to the power of x. All exponentials, positive exponentials, have the same sort of graph. So y equals 5 to the power of x would have a very similar graph. It would also get closer and closer to 0, like this. It would also go through the point 0, 1, because anything to the power of 0 is 1, but it'd just get bigger a bit quicker. It'd go up a bit faster like that. So that's what the graph of y equals, say, 5 to the power of x would look like. Has the same general shape, they just differ in how quickly they get larger. And the larger the number is, so the larger the value of a, the quicker that the function will go up, the quicker the y value will increase. Okay, let's now look at the second one, 2 to the power of minus x. So I'll graph that in green. So it's sort of the same, except the values are reversed. So at minus 4, we have now the y value is 16. Then we have minus 3, 8, minus 2, 4. And then we have minus 1, 2, which is there, still goes through the point 0, 1. The y-intercept is still 0, 1. Now it starts to get smaller, so it's doing the opposite to the blue function. It got really large, and then it gets really small, rather than the other way round. So 1 1/2, again, you can just estimate these. It just gets closer and closer to 0, but never actually hits it. So that in green is the graph of y equals 2 to the power of negative x. It's actually a reflection. So the green curve is a reflection of the blue curve, and they are reflected about the y-axis. So y equals 2 to the power of negative x. If you had to graph that, we could have done it quicker. Rather than plotting all those points, we could have just reflected the blue graph about the y-axis. All right, so for the last one, we could plot all the points again, but a quicker way is to do it is to look at the blue graph, y equals 2 to the power of x. So as I said before, what's happening here in this table of values down the bottom is that each number is the same as the blue graph, except it's become negative. So I'm going to graph this in yellow. So we saw that the point here, 416, on the blue graph, so it would go down to 4, negative 16, which we won't be able to see on this graph. This point here, 2, 4, it would go down. It'd be reflected about the x-axis. So x value is the same, but the y value becomes negative. This point here, we make it a negative. And this point here, we make it a negative, and so on. So what you can see, rather than plotting all the points, you might be able to see that it's just going to go like this. So same as the blue graph, it will get closer and closer to 0 as x gets more negative, but it will never hit 0. And then it gets, this time, really negative, a large negative number really quickly. And that's the hallmark of exponentials. They get big really quickly. So this will be the graph of y equals minus 2 to the power of x. So notice that the yellow graph is also a reflection of the blue graph. The yellow graph, though, is a reflection about the x-axis. So the line of reflection from the blue graph to the yellow graph is the x-axis. The line of reflection from the blue graph to the green graph is the y-axis, okay? So all exponentials have the same general shape, so there are quicker ways that you can do it. I just wanted you to understand why the shape is as it is. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.